Welcome back. So the good news is you've done really well in the midterm. So congratulations to you. We haven't finished grading it all yet, but based on the multiple choice, everyone did spectacularly well. Yeah, the average is way up in the high 70s. It's approaching 80, and very, very few people did much poorer than that on the multiple choice. So, great job. Yeah. Whatever you're doing, keep doing it. The final exam is not going to be much harder than the midterm at all. It's just longer because it covers more material. And the material at the end of the course, is it harder than at the beginning of the course? No, I don't think it's harder. Maybe there's a few more details to learn about, but the principles are the same. So if you keep on doing what you're doing, do the readings, go over the material before class, ideally, or if not after class, come to class, come to lab tutorials, ask questions, then you're going to do very well. And the administration will be very unhappy with you that this course isn't more of a filter, but that's good. Are there any questions before we start in on today's material? No, I don't see any. Just about the midterm grades, I think we'll probably have them all graded by, I'm hoping by the end of this week, but it might take a weekend. So for sure by this time next week, we should have the grades all sorted. And if you have questions about your grade or questions about any answers or how they were graded, your first stop is to go talk to your TA of your lab tutorial. And if you get no joy from talking to them, then you can come talk to me. And we'll sort it out. Okay, last time we talked about one-way ANOVA and a variety of topics around one-way ANOVA. And after last class I posted this cool Happy Valentine's Day. It's old now, but there's some R code that will actually draw a heart. So R can do more things than just steps. Today we're going to follow up one-way ANOVA, and we're going to talk about what to do after you get a significant omnibus F test. Remember, in one-way ANOVA, we're testing multiple groups, not just two, like in a t-test, but multiple groups. And the first test that we get from the ANOVA is that omnibus F test. Omnibus is a word that means all together or as a whole. So it's a test of the null hypothesis. Do you remember what the null hypothesis is for one-way ANOVA? Anyone want to say it out loud? What's the null hypothesis in just everyday language? Yeah. That's right. How should I say it properly? The population from which each group was sampled has the same mean. Yeah. So in a way, it's saying all groups are the same. They all came from the same population. That's the null hypothesis of the omnibus test. So if that omnibus test tells you that null hypothesis should be rejected, it's basically telling you at least one of those groups was sampled from a population with a different mean than the other groups. At least one, if not more than one. So when you find that out, that's nice to know. Good. But which one is it? That's what we'll talk about today. Let's go to the slides. Alrighty, so remember what the linear models look like for a one-way ANOVA. This is an example where we have three groups. The null hypothesis corresponds to the following linear model, where we're proposing each observation, the ith observation in the jth group, comes about from one single grand mean plus random variation. And that's represented graphically by this single horizontal line that cuts across all three groups, the red group, the green group, and the blue group. That's kind of a mathematical and a graphical way of saying what I said before. The proposal for the null hypothesis is that all three groups came from a population with one mean. And any deviation around that mean, whether it's within a group or across groups, any deviation is just random variation. The alternate hypothesis says no, that's not true. What I'm proposing in the alternate hypothesis is that the ith observation in the jth group came about from population mean for each group plus random variation. And so graphically, we can depict that with a separate horizontal line, one for each group. So in the null hypothesis, what's the value of that single population mean? We don't know. We haven't measured the whole population. We've just taken a sample. And our best estimate is the sample mean. In the alternate hypothesis, what are the values of these three population means? We don't know. We didn't sample the whole population, but our best estimate is the mean of each sample. So mu sub 1 would be 3, mu sub 2 would be 5, and then mu sub 3 would be 7. So that's the way I like to think about ANOVA in terms of a null hypothesis, an alternate hypothesis. This would be called the full model. This would be called the restricted model. It's basically a proposal of how many parameters we have to estimate. Here we have to estimate one parameter, mu. Here we have to estimate 3, mu1, mu2, and mu3. So when we get that onto this f-test, we get a p-value associated with it. And that's what we refer to as that's the number based on which we talk about statistical significance. And so this is a definition I like of what the p-value is. It's the probability of observing a difference between groups as large as the one that we did under the null hypothesis. So it's the probability, if the null hypothesis is actually true, it's the probability that we could have ended up with sample means this different, even if they all came from the same population with the same mean. Right? There's always some chance I could just be unlucky and pick 5 low scores in group 1, 5 medium scores in group 2, and 5 high scores in group 3, just through random sampling. It could happen. What's the chance of that? That's what the p-value gives us. And so it's a metric of our it gives us an idea of how likely is it that these data could have come about if the null hypothesis is true, if the drug doesn't work, if this is just dumb luck that I happen to pick people that had lower blood pressure in the drug group, not because of the drug, just because of random sampling. That's what the p-value tells you. I want to talk about effect size briefly, because that's a different concept. It's related, but it's a different concept. The effect size gives us a measure of the magnitude of the difference between groups. And sometimes that magnitude of difference between groups is normalized by the within-group variation. It takes into account how much variability there is within groups as well. So it's a metric of the strength of the effect. The p-value is a metric of our confidence in whether the null hypothesis might be true or not. But effect size is a more direct measure of how big the difference is, how big the effect is. So here, I searched for an actual graphic online and I couldn't find a good one, so I just drew one. And I'm a terrible artist. Some of the drawings look like those drawings, but like people with brain damage. It's true. I'll show you a pretty one next time. So here's a sort of 2x2 grid. We have statistical significance, which could be low or could be high across the top, and we have effect size along the rows. A small effect size and a big effect size. And so the effect size basically, and these are distributions of scores in 2 different hypothetical populations. So the difference between the peaks of these Gaussians are the average score in those populations. And so the difference between these peaks here and here is the same. I call that D. The distance between these peaks is 3.0 here and here. So in both cases, it's a big effect. This might be placebo and this might be drug. The difference between placebo and drug on average is the same in both of those situations, and it's big. Here, the difference between the peaks is small in both cases. And I've called that D, and I've said maybe that's 0.2. So that's effect size, which can be small and big. Now, independent of the effect size, is the p-value you might get if you did a significance test on those two groups. And so you could have high significance, p less than 0.001, for, let's start here, for a big effect. D is 3, it's a big difference between these, and the p-value is really tiny. And it's really tiny because the width of these distributions is very narrow. The variability within each population is small. So the relative difference between the distance d and the width of these distributions gives you a metric of the p-value, basically. So you can have a highly significant effect that's a big effect. D is 3. If the standard deviations of those populations are small enough, or, and I haven't drawn it here, or if n, the number of samples you take from the population is big enough, you might end up with a similarly highly significant effect, but the actual magnitude of the effect is small. And some of there are examples of this out there. There are some, these studies of things like, one example is differences in spatial reasoning between males and females. It's kind of become a mythology. Oh, males are just better at solving spatial puzzles. That's why men can parallel park better than women, which is totally false, by the way. Those kinds of studies were based on huge sample sizes, tens or hundreds of thousands of people taking these sort of tests of spatial abilities. And so they ended up having, for instance, this is a good example, a very highly significant difference, right? And that's what you read in the newspaper. Researchers discover highly significant difference between males and females in whatever, right? And they're referring to the p-value. When you actually go and look at the difference on whatever scale is being measured, it's actually a tiny difference. In those kinds of studies, if you look at the distribution of scores, you have this really broad Gaussian for males, and then a really broad Gaussian for females, and one is just like slightly shifted over. Tiny, tiny difference in the actual score. But because the sample size is so huge, the p-value is very small. And so the p-value says, I'm extremely confident that the difference is not zero. Right? Remember, it's a test of the null hypothesis. So it's true, it's a highly significant difference, but what it really is, it's a highly reliable difference that's not zero. Is it a big difference? Maybe, maybe not. And in that case, it's not. In this case, it's not a big difference, it's a small difference. In that case, it's a big difference. And then, of course, you can have a small effect size, mean 0.2, but because these distributions are very broad and the sample size is small, you don't get you get a small statistical significance, or maybe that turns out to be not significant. So you can get all combinations, right? You can get a highly statistically significant result that's actually not a very big effect. You can get a non-significant statistical result, or a situation where there actually is a big effect, but because you didn't have the statistical power to detect it, your p-value is insignificant. And then every combination in between. So on the website, I put up readings that point to readings you can do about effect size. And make sure to do that, because those are two concepts that are easy to get mixed up, the p-value and the effect size. And going forward, whenever you see a story in the news or you hear about some highly significant difference or highly statistically significant finding, try your best and go and find the paper. Go and find the paper and actually find where that statistical test is reported, and see if they report the effect size as well. These days, journals are asking people to report effect sizes along with significance tests, which is a good thing. And dollars to donuts, you'll find a very small p-value, and then a statement that it's a highly significant difference, and then you might find actually a a small effect size, which should give you a pause. So before I go on, are there any questions about that, sort of those two concepts? They're completely orthogonal to each other, the p-value and the effect size. Yeah.
Does the overlap between the two distributions, is that related to statistical significance?
It is, yeah. The overlap of the distributions relates to statistical significance. It also relates to effect size in the sense that the distance between the means corresponds to the overlap. Really, the way that the overlap affects the p-value is the overlap taking into consideration the width of the distributions as well. And also the sample size, which I didn't put here. There would be a third dimension you could draw on this chart, which would be small samples and big samples. Yeah.
And in case, if we were trying to study it and we have like a low or relatively low significance, by a really large effect size, we just need to like replicate or increase our n.
Yeah, that's a great question. If we have low statistical significance, or maybe it's just shy of being significant, maybe it's 0.051, but we have a big effect size, then it's sort of asking me, like, what do you do next? If it was me, I would collect more data. As the sample size gets bigger, all other things being equal, the p-value will get smaller. If the effect stays the same, right? If you collect more data, then the denominator of that f test is going to get smaller, and so f will get bigger. Yeah. But, be a bit cautious. If you collect some data and you get a p-value that's just shy of significance, 0.055, it's tempting to think, ooh, it's almost there. If I just get more data, it'll slide below 0.05 and I'll be good. Maybe. Maybe not, right? If the alternate hypothesis is true, then yes. As you collect more data, the p-value will slide lower and lower and lower because the effect will stay the same. If the null hypothesis is true, then more data will still get you closer to the truth, but it'll get you closer to the truth that there's no difference, and the p-value might increase. Yeah. We'll get to that in a second when we talk about distribution of the p-values. Okay, in terms of the actual metrics of the effect size, there's a host of different metrics that people use. One of the common ones is called eta squared. That little symbol is called eta. And it's a measure of effect size, and you compute it by taking the sum of squares between groups and dividing it by the sum of squares total. So it's basically a proportion of the total variance that is explained by the levels of the factor. That's sum of squares between. And it can range between 0 and 1, just like an R squared can. It's a similar concept. And there's a package in R called effect size, and there's a function in there called eta underscore. There should be an S there. Squared, not eta squared. We'll give you eta squared. So that's one measure of effect size. And you can see how it works. The SS between is kind of like the distance between the means of those distributions. And the SS total is kind of like that plus the within group variation as well, the total variability. So if you imagine two scenarios where the SS between is the same, but the SS total is big in one case and small in the other case. The case where the SS total is smaller, you'll get a bigger effect size. Some researchers prefer this other metric called omega squared. And the reason they prefer it is they say that it can be less biased than eta squared when you have small samples. And small samples is like 10, 15, that kind of thing. And in R, there's a function called omega squared in the library effect size that you can use. You can read about how it's actually computed in the readings. It's a similar concept. That third one is called Cohen's d, and it's another measure of effect size, and it's simply the ratio of the difference in means on the top and the standard deviation within each group on the bottom. So a very similar concept to sum of squares between and sum of squares total, but a bit more directly focused on means and standard deviations. I put some links at the bottom to a variety of places that talk about how to interpret those effect sizes. What is a big effect size? What's a small effect size? What's a medium effect size? There are just rules of thumb. There are no like cutoffs like there are for 0.05 for alpha. There are just sort of ranges that people talk about.
Yeah. The Cohen's d, the standard deviation, the groups, is that like of your entire sample or the?
Yeah, that's a good question. So what do I mean by standard deviation of the groups? Usually it's what's called a pooled estimate of the standard deviation of the groups as a whole. So each group has its own standard deviation, and you do something to kind of average those. Yeah. So it's kind of like the average standard deviation of each group. Okay, so that's effect size. The concept is simple. The concept is basically the difference between the groups normalized somehow by the variability within each group. All three metrics do essentially the same kind of thing. Okay, let's go back to the ANOVA. Let's say we've got an ANOVA on this hypothetical drug data set from the Navarro text. We've got three groups. Placebo, and then two drugs. These are fictitious drugs, anxiety-free and joystick. And the score, the dependent variable, is some measure of how much your mood improved. So it improved a tiny bit with placebo, and a little bit more with anxiety-free, and even more with joystick. If we do a one-way ANOVA on that data set, and you can do it yourself by loading the data from last time, we get a significant F. Our F statistic is 18.6, and our p-value is 8.65 times 10 to the negative 5. That means 0.0000865. The way to remember this E minus stuff is whatever that number is, there's one fewer zeros. So e to the minus 5 means there's 4 zeros and then the number 0 point and then 4 zeros and then 865. So it's way less than 0.05. So there's a significant omnibus F, which tells us we should conclude the null hypothesis is not true. It's not true that all three groups were sampled from a population with the same mean. Okay, good. So what could it be? The basic answer is we're going to conduct follow-up tests, which are sometimes called post-hoc tests, to find out what's different from what. But let's talk about what the different alternatives could be, because there's a lot of them, right? Possibility one is the null hypothesis is true, where if you tested placebo against anxiety-free, they would be the same. Placebo against joystick, they'd be the same. Anxiety-free against joystick, they would be the same. Right? With three groups, we've got three possible pairwise tests. This one, and that one. Or it could be that those two tests show the same, and then anxiety-free is different than joystick. That would correspond to one of the alternative hypotheses. And then there are a whole bunch of other alternative scenarios that could happen, right? There's only one null hypothesis. Everything's the same. But there's a whole bunch of possibilities for the alternate hypothesis. And that's our job after a significant F test, is to find out what's going on. There's a function in R called pairwise.t.test, which will perform pairwise tests. We just give it the variable that codes what group they're in, and the variable that codes their score. We tell it how to adjust the pairwise tests, which we'll talk about in a minute. If you don't want to adjust them, you just say none. And it gives you a matrix of p-values. So placebo versus anxiety-free, p is 0.15, not significant. Placebo versus joystick-ham, it is significant. Anxiety-free versus joystick-ham, it is significant. So basically it's telling you that placebo is not different than anxiety-free, but placebo is different than joystick-ham, and anxiety-free is different than joystick-ham. So pretty simple. The idea is you just sort of follow up a significant F test with essentially pairwise t-tests. But there are complications, which we'll talk about now. That's the basic concept, but there's some things we have to take into account. There's a different function from the LSR package called post-hoc pairwise T, which is a little bit easier to use because you can just see that you're a ANOVA object. You don't have to slice out the variables from your data frame like you do here with pairwise.t.test. You can just feed it the output of your ANOVA and tell it how to adjust it, and it'll also give you the p-values. So that might be really easier to use.